Hey, not too many announcements. We have an assignment that is due tomorrow evening. I'll be getting up the next assignment over the material we're going to be covering over the next couple of days. This will be more of an implementation related assignment. I'll probably throw a couple of book problems related to the probabilistic reasoning that we were doing over the last few days. But the bulk of the next assignment will be implementing the balancing algorithm that we're going to be going over the next couple of days. Then I still push back the exam by the week. So instead of Friday, it'll be a week from Friday. You'll have a study guide by Friday, and anticipate someday next week we will have a review session after you've had a chance to look at that study guide, start studying, figure out what your questions are about the study guide, about the material, and we can have a review period next week. I usually do it the day before the exam, but if we like it to be a couple days before, I'm okay with that too. We'll vote on that early next week. Figure out what would be useful for the class as a whole. Last time we reintroduced the concept of a binary search tree. And we're going to motivate why we're going to care about this process that we're going to call balancing. This is not something that you handled in data structures if you took data structures here. And it's something that's very important for the entire reason why binary search trees exist, which is for efficiency. And if you don't maintain the balance of the tree, then you lose the logarithmic guarantee for insertions, deletions, and fetches. And we absolutely need that logarithmic guarantee. Otherwise, this might as well be a linked list. And I'll talk about that more in a little bit of detail here in a second. So binary search tree, the reason that we care about binary search trees is they allow for insertions, deletions, and gets all in logarithmic time. All we have to do is compare, is this node greater than or less than the query? And that eliminates half of the search space, assuming the tree is balanced. So from the root node, we ask, is the query greater than or less than 10? And we take out either the entire left subtree or the entire right subtree. And recursively, we will ask that same question over and over, taking however many nodes remain and have them, as long as, again, we have a balanced binary search tree, which means there are approximately as many nodes in a left subtree as there are in a right subtree. So the question I have for people is this always true with a binary search tree? Now, if we allow for the binary search tree to not be balanced, if we're not checking for and handling that there are approximately the same number of nodes on a left subtree as a right subtree, do we get that logarithmic guarantee?
I don't think so.
We definitely don't. Think of a particular insertion order where we're going to insert the nodes from smallest value to largest value. What happens if we wanted to just insert the nodes 1 through 5, but we're going to start with 1 and then get to 5. So the root becomes the first node we add. That's going to be our 1. When we try to add a 2, we will ask, is 2 greater than or less than the 1? It's greater than, so it's going to become the right child of that 1. When we insert 3, we start back at the root and say, is it greater than or less than the root? It's greater than. Is it greater than or less than the 2? It's greater than, so we insert it as a right child of the 2. And this process continues. And we end up with, does this look like a binary search tree?
No.
It looks more similar to something else we've seen before. What does it look more similar to? A linked list. So in the worst case, an imbalanced binary search tree is a linked list. What were the complexities of insert, delete, and get in a linked list? Linear. So we don't get this logarithmic guarantee, which is the entire purpose for having this binary search tree in the first place. So why implement a binary search tree if we're not going to worry about or consider or implement balancing? We need that logarithmic guarantee. And that means that as we go through the insertion and deletion processes, we may need to make some changes to the tree in order to have it maintain that balanced nature. So yes, the order of insertion matters, but rather than trying to know all of the data and insert them in such an order that maintains that balance, we can go through a process that allows us to maintain balance on an insertion or deletion basis. So we'll talk about this for a second. So to guarantee the log access, I already spoiled this as I tend to do. So the left subtree depths cannot vary significantly from their right subtree depth counterparts. And in this case, significantly just means they have to remain within a constant factor of each other. The two different algorithms that we will discuss, we're only going to study one of them in detail, but there are two reasonable algorithms for balancing a binary search tree. One of them says that the left subtree cannot be more than half or twice as deep as the right subtree. That's the one we're not going to study. The one we are going to study says that the left subtree depth and the right subtree depth cannot vary by more than 1, plus or minus 1. So it's a much tighter bound on what we're going to declare to be balanced. So those are the two algorithms, ABL and red-black. So the one we're studying, ABL, there is no left subtree that varies more than plus or minus 1 in depth from its counterpart right subtree. And red-black just says twice or half. So times are divided by 2 rather than plus or minus 1. And to make sure that this stays true after we insert or delete, because again, we don't always know all of the nodes that are going to be inserted or deleted at a particular moment in time. We have to check after each insertion or deletion that this is still true for every node in the tree. But the process of this check can't be horribly inefficient, because if the check is inefficient, then it might take as long to check whether the tree is still balanced as it would be to do that insertion, deletion, or get if it were a linked list instead of a binary search tree. So we're going to place a cap on how complex this check can be at the logarithmic time guarantee that we want the binary search tree to have. So checking whether it's balanced and balancing both cannot take more than the logarithmic time. Does that make sense as to why? We'd have a two-step process. Insert and then check whether it's balanced. And if we're going to get that nice, well, if it's balanced, then the insertion takes logarithmic time. If it takes longer than logarithmic time to verify or check whether the tree is balanced, then you might as well have a linear time algorithm anyway. So that places a constraint on us that we need to make sure that logarithmic time is the cap to how long this will take. So yeah, if the tree is no longer balanced, then we have to somehow manipulate and change the underlying structure of the tree in order to be able to say again that it is balanced by the condition of either ABL or red-black, whether it's plus minus 1 or times divided by 2. We would need to make sure for every node in the tree that that balance for its subtree is maintained. And in fact, both of these algorithms do that in that logarithmic time guarantee. So let's talk about why there are two algorithms for this. Why would it make sense to have two different approaches? As we find in computer science, if there's one approach that's just strictly better than the other approach, we don't really consider the other approach, ever. Really, the only thing that I can think of that does this is sorting. And the reason we introduce things like bubble sort, selection sort, insertion sort, is that they're easier to learn, not that we actually ever use them. They're too inefficient. So as always in computer science, there's a trade-off between two algorithms that are used for the same purpose. And that boils down to what happens if the bound is tighter on a left subtree and a right subtree. If we only allow plus or minus 1, what does that improve on over a left subtree versus right subtree that is times or divided by 2? What is better about a tighter guarantee? Yeah. It's consistent. You can place it's a better kind of worst case guarantee by a constant factor, but what is sped up when we have that? It's the guess. The deepest answer, the deepest search is going to be, instead of 2 log n, it's going to be log n. So gets are more efficient when we allow, or we don't allow the left subtree and right subtree to vary by much. On the other hand, what is the benefit of allowing one subtree to be twice as deep as the other subtree? Yeah.
Go faster.
Insertions and deletions are faster because we actually don't have to. It is going to be a less frequent that we break that. There are more places now to insert or delete that don't violate that constraint. So more frequently when we insert and delete, we don't have to go through this rebalancing process. So yeah, it's basically access time versus insert and delete time. Now, this doesn't change the asymptotic order of either of these. It just makes them about twice as efficient. So you will make gets twice as efficient, making inserts and deletes take twice as long, or inserts and deletes will be on average about twice as efficient, and the gets will be about twice as long. So a constant factor either way, but you can imagine a situation where you're designing a system, and the difference between this system and other systems are that we have all of the storage that we're ever going to need now. And we just need to create the storage structure that's going to allow fast access to that structure in the future. We're not going to be inserting or deleting, but we're going to be doing lots of gets. In this case, you would want to make your binary search tree balanced with AVL because the subtree depths are much closer to each other and shallower on average, so your gets will be faster. You won't be doing very many inserts and deletes, so the downside of AVL is minimized because of the situation that you're applying it to. On the other hand, maybe this is a database that has a lot of changes to the table, but not very many access requests. So it's storing something, and every year we pull the information from the database, but every day we update the information in the database, in which case we're doing a lot more insertions and deletions than we are gets. So that would tell us that we should implement that storage with red black rather than AVL. So there are reasons to know both of these algorithms, but I find that if you know and have implemented one, the other one makes a lot of sense. In general, AVL is easier to understand and a little bit harder to implement. Red black is much harder to understand and a bit easier to implement. So I'm going with the little bit easier to understand, a little bit more challenging to implement, because I think a struggle a lot of the time when you're learning something is just getting that initial grasp of the concept. And then it also provides really good practice when you go to implement it to have the more challenging implementation just by a little bit, because you'll get stuck a little bit more, ask more questions, learn a little bit more from it. And it generalizes to where if you can implement AVL, you can implement red black. So this summarizes everything I just said. So we're trading off access time versus insert and delete time. But the constant factor there is just twice or half the speed. Does not change the asymptotic order. I talked about different applications prioritizing one or the other, telling us that one of these would be a slightly better implementation than the other. But talked about a little bit about an application of each. So we're going to, from here, jump into reviewing how insertion and deletion work in binary search trees. So we're going to do that. Let's build a tree. Somebody give me a number.
32.
That's going to be our root. Someone give me another number. That's going to be a left child of 32. Someone give me another number. 100. Someone give me another number.
25.
Couple more.
I like it.
One more.
32.
38. All right, we agree with this construction so far.
So far, yeah.
Okay, so I went through the insertion algorithm in my head, adding these in, but let's come up with one more number and look at in detail how we would insert that node into this tree. So one more number. 11. First thing, is 11 greater than or less than 32?
Less than.
Less than. We move to the 7. Are we greater than or less than the 7? Greater than. We move to the 25. Are we greater than or less than 25? Less than. Greater than or less than 16? Less than.
Yeah.
We can see that insertion order matters here.
Yes, it does.
The exact tree that we construct, and we can see that we're not really getting that guarantee. Where are nodes where there is a particularly bad imbalance between the depth of the left subtree and the depth of the right subtree? What's the worst offender here?
Probably 100.
It's on the 7. If we look at the left subtree and the right subtree of the 7, what is the depth of the left subtree? 0. What's the depth of the right subtree? 3. So 0 versus 3 is going to be violated whether we have times or divided by 2 or plus or minus 1. So this would tell us that there's an issue here. We should try to equalize or closer to equalize the depth of the right subtree and the depth of the left subtree here. You can imagine what that would look like. That would take the depth of this tree. And if we take some of the nodes that are over here and we move them somehow over here, we're reducing the depth of the tree so that accesses are faster. And now we wouldn't have to, in the worst case, query 11 and look at one comparison, 2, 3, 4, 5 before we say, yes, we found the 11. And if we had done something that reduces this depth, that increases this depth, we could answer that in 4 comparisons rather than 5, or 3 comparisons rather than 5.
Okay.
So that's kind of the thought process behind trying to make sure that this is as full as we can get it within those guarantees. It has to be a logarithmic time process. So in general, for insertion, you just start by comparing it to root, and insertion is pretty straightforward. But deletion is a lot more challenging. How would we handle, so we had 3 different cases for delete. Do we remember what those 3 cases were?
Familiar.
It has to do with a variable that can take 3 possible values. The number of children of the node to be deleted. There was a 0-child case, a 1-child case, and a 2-child case.
I don't know if we went over that one in data structures. It does feel familiar though.
Interesting. Okay, good to know. I will start from there. So the 0-child delete case, what is a node here that has 0 children?
11.
11. If we wanted to delete 11, what would the process be for deleting 11? What's the first thing that we would need to do? Navigate to it. Right.
Yeah.
We need access to this node. And if we have this structure, all we have access to are the fields of the structure, which is usually just the root. We don't store immediate access to every node. Otherwise, this structure would explode in memory. And we would have to keep track of the entire structure in memory for fast access to every single node. And that's going to be a challenge. That makes things like passing this tree very difficult between scopes. So if we wanted to delete the 11 with their 0 children, we would just navigate all the way down to the node and delete it. Are we okay just removing the 11? What happens if we delete the 11? We get rid of this node. What is 16's left child? Is it some value? Does it still anticipate that it's pointing at something?
No.
It becomes null
No.
when we delete it. So this is everything that we need in the 0-child delete case. But that won't be the case when we look at 1-child or 2 children deletion cases, because we will need to modify where the parent's reference is when we look at this 16's left child being some node. If there's another node that it needs to point to, then we need to have access to the parent when we do this iteration. So in the 0-child case, that's great, but when we choose to delete something, we don't know how many children it's going to have. So we don't know which case we're in until we go find the node. So because of this, when we do the process of moving down and finding that node, we also keep track of the parent. So we have two nodes that we'll call current and parent. And we're going to start both pointing at the root. The very first thing we do is we move the current, but without changing where the parent is. And then we just continue to move them one at a time. The child and the parent both update at the same time. Parent becomes child, child becomes either left or right child of the child based on whether it's greater than or less than the current node's value. Okay. Questions on that? So that's the zero child delete case. We'll pretend like we deleted the 11. What about one child delete? What's a node here that has one child?
25.
25. Let's look at deleting 25. So we would navigate as such, 32 with 32 with parent and child. We would have child update since 25 is less than 32 to be its left child. Then we would look at, is it greater than or less than the 7? Parent would become child, child would become child dot right. And we see that the child is now the 25. So if we had access to the parent, we can see that the current node is the parent's right child. So we want to change this parent's right reference to become the child that is this child's either left child or right child. It doesn't matter since it has one child. You know, it either has a left child or a right child. But regardless of which one it has, it's still greater than the 7. So it belongs as the 7's right child. It's going to replace the one child node that we are deleting. As we get rid of this 25, we want to redirect this 7 to be that 16. So in code, the first thing we should do is we should update this 7's right child to be current left child. If we do that, we just have a couple of if statements. So we would have parent dot set right, probably set right child. To the current node dot something like that. We're gonna, since these are going to be fields of nodes, they're gonna know who their children are. We're going to say parent dot set right child to be cur dot get left child. And as we do this, now there's no reference anymore to this node 25. We don't actually have to go delete it. There's just no reference pointing to it, except for cur. Cur is still pointing at this node, so it is not technically deleted. But when this method ends, that is this deletion method, since cur was declared locally in that scope, that means that cur goes away. As cur leaves scope and this goes away, there's now no reference to this node anywhere. So Java's garbage collector will come suck up the 25 and free that memory. And that is now our tree. So no further information or work is necessary to do that. So the one child deletion case is also fairly straightforward. Questions on one child delete? Regardless of which child the parent is, you're always going to replace that child with the child you're deleting's only child, left or right. That will always be the case. You'll just need a couple of statements to figure out, are we setting the left child or the right child? Is the child the left child or the right child? So you just have different conditions within an if statement for whether we're setting the left child or right child, getting the left child or the right child. Okay, two child delete. What's a node here with two children? 32. We're going to delete the 32. We can imagine there's a little bit more work here that we would want to do. I don't really want this to be the root node.
Yeah, well,
I feel like we could probably do something.
If we can reverse it and it got rid of 100 last time. That'd be
Yeah,
For 7 instead.
I actually want to make this a little bit deeper, just so we can see. Okay, I'm gonna delete 7. Because this makes this kind of as reasonably complicated as possible, so we can see all of the elements that we would need to consider when we delete with two-child delete. Sometimes it's a little bit more straightforward than this, but there's no way to know that ahead of time. So to delete the 7, we first have to figure out how we are going to, there are 2 ways to do this. We can either replace the 7 with the next smallest or the next largest node. Which one do we want to use? Bias with smaller, bias with larger.
Doesn't matter.
It does not matter.
I think larger might.
Larger?
be what
Sure,
we're looking for, but I'm not sure if I'm right, actually.
that is fair. So you're either going to look for the next node in this tree that is larger than this 7, or the next node in this tree that is smaller than this 7. Regardless, it's one of these 2 nodes. And the way we get there is if we're looking for the next largest, we're gonna go from this node with 2 children, we're gonna go to this right child, and then as far left down that subtree as we can go. We agree that that process guarantees that that is the next largest number in this binary search tree. We know that it has to be larger than the 7, so we have to be going down the right subtree. But we want the smallest number that is larger than the 7. So that's always going to be going down the left subtree as long as it exists. If we ever go down a right subtree, then the node we were just at is smaller than its right child. So as long as there's a left child, that will be smaller than the current node. And that guarantees that when we go greater than, but then the smallest possible value that is greater than down left child, left child, left child, you get to that node that is the next largest.
Fascinating.
So all we're going to do here is we are going to swap the 7 and the 15. And then recursively delete this 7. Now we don't know this has no children. This could have a right child, but we know after we recursively delete the 7, we're no longer in a 2-child case. If we were in a 2-child case, this would have had a left child. We would have gone there. Because it's still greater than what was the 7 and less than the number that we were going to delete. So it's either the recursive delete is either a 0-child or a 1-child delete, which is much more straightforward. So we can now just remove the 7 and everything in this tree still works. Much easier. One other way you could have done this is to actually delete this node. And if you delete the 7, you can do something like replace it with its right child, the 26. So if you kind of change this left to be that, change this left to be that, we've orphaned this node. So this right child is now, this node's gone, but this child has no home. So we need to now reinsert this node and its whatever subtree it happens to be into the tree, which is going to become the right child of this 6. That becomes the 15.
Wow.
That works as well. I find the swap recursively delete to be significantly easier in practice as well as to understand, but those are 2 different ways that you can do that. Okay, so that's a bit of a recap on insertion and deletion.
Thank you.
Insert is always the same process. Delete depends on the 3 cases, 0-child, 1-child, 2-child, and you handle the logic differently depending on how many children the query node has. So we looked at cases for deletion as 0-child, 1-child, 2-child. And this stays exactly the same for balancing. We're not changing the actual insertion or deletion process. But we will need to do something extra at the end of insertion or deletion to ensure that balance has been maintained. So what we're going to introduce here, if you've implemented a binary search tree in data structures, if you have access to one of these structures that you've made, then you've coded an insert and a delete. And that's great. You will not need to rework any of that. We're just addending to the end of it to ensure that the tree structure that we have after that insert or delete is balanced. So yeah, balancing happens after a successful insertion or deletion. And after we do that, the fact that we inserted or the fact that we deleted may have changed some node in the tree's balance and made it imbalanced in a way that we need to fix. But the reason AVL works, and we don't have to default to red-black, is the relative balance after a single insertion or deletion can't change by more than one. So a node that was imbalanced ever so slightly at plus or minus one, which is allowed, as soon as we reach that plus or minus two, that happens, we can't get to a plus or minus 3 or 4 or 5 off of a single insertion or deletion. It's going to change the relative balance of each node by at most 1. So if we can do that, we'll just recognize that the change that happened had to be along the path of the insertion. If we went left child, right child, left child, and then inserted, the imbalance that we created had to be along that path of insertion. There's no way we changed the relative balance of some node on the other side of the tree from that insertion. It would either have been at the root's child, whichever path we went down, its child, whichever path we went down. So we only have to look at the logarithmic number of nodes that were on the path of the insertion or the deletion. Does that make sense? Kind of, sort of, couple nods, a lot of blank stares. Let's see if I can craft an example. I want something that starts out balanced and becomes imbalanced. So we'll make this as relatively easy as possible. So here's an example of a currently balanced binary search tree, even according to AVL. How do we know this? Look at the root. Its left child is depth 1, right child is depth 2. That's plus or minus 1. That's allowed. This node has no children, so its relative balance is equal. This has a single child on the left and nothing on the right, plus or minus 1. That's allowed. So this tree is balanced according to AVL. But imagine now having another insertion that inserts here as this node's right child. There becomes an imbalance in the tree. In fact, there's an imbalance here and here in terms of the relative depths of left and right subtrees, but it was on the path of insertion. When we went to go insert this node, we went down those exact nodes that created the imbalance. And if we could do something like make this node go here, this node go here, and this node go here, then we would again have that balance. So what we've found as we've done this is that as we do that logarithmic time insert, we have a logarithmic number of nodes to look at as to whether they're balanced or imbalanced. Since that takes logarithmic time, we just have to define a constant time process for rebalancing. And I will assert that we can make that change with really 3 comparisons, 3 steps. Okay. Questions on any of this so far? Right, so we are going to define that process that I just drew. We call them rotations.
Oh,
To rotate, we're going to change the relative position of nodes in the tree without adding any more nodes or removing any nodes. We're just changing where they are in the tree with the goal of fixing an imbalance. If anywhere there is a node with more than plus or minus one with its relative depths of left or right children, then we will do some kind of rotation at that node in order to change that plus or minus two into a plus or minus one. There are 4 cases of rotations that we need to consider, but they're relatively similar to each other. If you understand the concept of one, it mostly makes sense that all of the cases line up with the same kind of logic. So we have a left rotation, a right rotation, a left-right rotation, and a right-left rotation. I'm sorry for anyone who's dyslexic here.
Interesting.
We'll also, when we talk about those node depths of their left subtree and right subtree, we're going to call the balance factor the left subtree depth minus the right subtree depth. So now we have a way of using the sign of the balance factor to figure out whether the left subtree is deeper or the right subtree is deeper. Something that is positive says there is more in the left subtree than right subtree. Something that is negative says there's something more in the right subtree than the left subtree. Since we're taking left subtree depth minus right subtree depth. So subtrees are imbalanced if the absolute value of that balance factor is greater than 1. Makes sense. Let's visualize cases for each of these rotations so we can understand how the rotation fixes the imbalance. So we're going to go in the order of these bullets. So we're going to start with a left rotation. So a left rotation is the case when a node that we'll call the parent has a balance factor of -2. So that means that the right subtree is 2 larger than the left subtree. And remember that it's not possible to be -3, -4, -5, etc. as long as we're doing the balancing after every single insertion or deletion. So we can hard code this at -2. It'll never be worse than that, assuming our code is correct. So how do we do it? We look at the parent's right child and look at its left child. If the parent's right child's left child is null, we can perform a left rotation. So it looks something like this. Here is the parent. The parent's right child's left child is null. So there should be, from the parent, a right child and then another right child. This is what creates that balance factor of -2. Left subtree depth is, in this case, 0. Right subtree depth is 2. It could be that the left subtree depth is 1, the right subtree depth is 3. Regardless, the difference is going to be 2. But in its simplest case, we have something like this. And we can see that it is imbalanced. How would we fix this? Which node color should become the root if we want this tree to be depth, at most a root and a level below it? We're not going to change any of the values of these nodes. They have to stay the same.
Thinking of green. If I'm
Green should be the new root, right? Because then the green's left child, meaning it's less than that, will be orange. And its right child that's greater than that would be blue. So we call it a left rotation because we're rotating counterclockwise around that parent node. Its right child will become it, and it will become its own left child. So the end result looks something like this. And we can see the balance factor after that left rotation is every node is balanced. We're back to the -2, we've changed that to a 0. Yes, we do need to cache the path taken for insertion or deletion. As long as if either the nodes are storing their parents, then we have a way to recreate that. So that will have a per node memory footprint if we do that. Or we could store the path taken as a sequence of node pointers or node references. How you implement that's reasonably up to you, but I generally like just storing a parent pointer. It makes your life a little bit easier when you're implementing it. Question? So end result of this, we added 1 to the depth of the left subtree and subtracted 1 from the depth of the right subtree. This was a trade-off that was absolutely worth taking because now, in the worst case, it took us 3 comparisons to identify that our search was blue. And now the worst case is it's going to take us 2 comparisons, the root and either the left child or the right child. So we've reduced the worst case search time. And this problem gets way bigger if we don't try to fix this as we go, because now instead of just subtracting 1 from the worst case performance, if we don't do that rotation, again, in the worst case, we end up with a linked list, and that drastically changes the asymptotic runtime of the get and the insert and the delete. Questions on the left rotation? In its base case like this, it's not too bad. So right rotation is exactly the mirror of left rotation. So we have our parent, balance factor is 2 instead of -2. So deeper nodes in the left subtree than the right subtree. We can identify the case by looking at the parent's left child's right child. Is that null? If it is, then we can perform a right rotation. So if the parent's left child's right child should be null. And we make a clockwise rotation that we'll call a right rotation around that root. And again, green comes up to be the new root. Orange becomes green's right child, and blue stays green's left child. And we end up with, again, something that is balanced from the identification of an imbalance. Questions on the right rotation and how it is the mirror of the left rotation?
I do not have any. Does anyone else?
Right. The slightly harder cases, they're only slightly harder. So we'll start with a right-left rotation. So the identification of a right-left rotation, we again see the balance factor as -2. So deeper nodes in the right subtree than the left subtree. So we now look at the parent's right child and look for its right child being null instead of left. I've bolded everything that is different. So different from a left rotation. This would be a left rotation if green were blue's right child instead of left child. But we still have a balance issue here. How should we fix this? Think about the relative positions of these nodes. What is a fix that would end up with something that is balanced from here? Exactly what we're going to do. I think by that you mean blue and green. If we're basically going to do a right rotation around blue, followed by a left rotation around orange. So step 1, we're going to do a right rotation here. This right rotation puts us in this position, which looks very familiar. This is the original left rotation case. So from here, we proceed with a left rotation, and we end up with 3 being balanced. So we've taken a 1-step process and turned it into a 2-step process, but the goal of a right-left rotation is to perform a right rotation on the child that puts us in the left rotation case, where we can proceed with that left rotation. So the left rotation is a subroutine of the right-left rotation. The only new thing that we need to do here is right rotate around this node, which if we have a right rotate and left rotate function that take a parent and child, you don't need to completely redefine this logic for every rotation type. You just need to do a right rotation around a node and a left rotation around a node. So you can call right rotate on this node and then left rotate on that node, and you're done. You only really need those 2 functions, right rotate and left rotate. It probably will shock nobody that the left-right rotation is the exact mirror of that case. So a balance factor is 2 instead of -2, deeper nodes in the left subtree. We look at the parent's left child and its left child. If that is null, we can perform a left-right rotation. So again, different from the right rotation, but we're going to create the right rotation case by left rotating the child.
Yeah, it does remind me a little bit of a mirror of the last case. But it's not quite.
So we're going to left rotate around blue, putting us in our original right rotate case. So all we need from here is a right rotation around the root, and we have a balanced tree. Did I say there were only 4 cases?
Yes, there were.
Haha.
Oh. But
As soon as we think this process is very easy and straightforward, let's take a look at a case where something strange happens when we do this process. We can end up with a process where we make an assumption when we do this, and that's that a particular node has at most 1 child. And if that node has 2 children, we end up orphaning one of its children and need to reinsert it. Let's take a look at what that means. So we could identify via some case here that we need to left rotate. The balance factor of this is going to be -2. We agree that it is -2. Depth of its left subtree is 0, depth of its right subtree is 2. If we just left rotate this, what happens?
one of them is going to get orphaned.
Yeah, the gray node gets orphaned. How or why? We do that rotation. Where does the gray node go? It's the left child of green, but when we rotate green to this position, it already has a left child of orange and a right child of blue. So it cannot be immediately attached to green anymore. So the solution is to reinsert that node where it belongs, which is as the right child of the node that got rotated down. And we know that that is free if this has no child here, but it may actually have a child here when we do this rotation, in which case we need to insert this node as this child's left child's right, until there is no right child anymore. In which case it belongs as the right child of that. This is going to be the next the next smallest node from here. We know it's greater than this, but it's the smallest greater number than that. So when this gets rotated down, it's going to be the smallest number that is greater than that. Like I said, right, I probably meant left. But it gets reinserted in that subtree where it goes. And exactly the same, we have a question. How would we have gotten to this state? Wouldn't we have triggered some kind of rotation before we got to this point? Quite possibly. So you can imagine that what got inserted here is something, in this case, it's absolutely right. There's no way that we inserted one of these nodes and got to exactly this position, but it is possible for a node to create this imbalance. Both of these nodes may have already existed, and if there were a node here, then the node that we inserted that caused the imbalance would have been either here, or here. Any of those would have done that process, and then the left rotation from here would still cause that orphaning. So it can happen, but that's brilliant to see that just with the tree as is, there's no way we could have gotten to this point without having done a prior balance. Okay, so same thing, but the exact mirror again is case 6. So we have something very similar, again, just mirrored. When we do the right rotation here, we're gonna orphan gray again and reinsert it on the other side of the tree. So we are out of time, as tends to happen. But we'll come back to this tomorrow and get a lot more experience with balancing. I will have us do some insertions and deletions and calculate where the imbalances are and go through the balancing process on paper, just so that you can get a sense of how that works. I have office hours starting now for any and all work or other class related questions. Hope to see a good number of you.
Well, it's kind of good in itself, too.
We're gonna implement ADs. The book goes over. I'm doing ABL.
This part is.